Okay, so these are the first pieces of the Tesla coil. These are the mains power. And I'm just going to explain them. So this one is the isolation transformer. This is all its information. And this one is necessary because basically it takes this AC power from the wall and uses the primary coil and the secondary coil to make a magnetic field here to send it to the secondary coil and then these outlet terminals. And so that's important, you know, because we don't want the test system to be interacting with the house's power. So we want it to be basically grounded to itself, you know. For example, here, let's look at this schematic real quick. Only the first part of it here. If you touch this, and this is all on its own, it's not grounded into the earth. It's for example on a table or something. It will not electrocute you if you touch it with one hand, because the electricity will not want to complete a path through you. You're not completing the circuit, basically. If you touch this, and this is switched on, you touch this, you are dead, because your body is completing the path through your hand, through your body, to your feet, to the ground, and you will die, because you're connected to the same ground that the huge copper ground rod of your entire house is connected to. So, if you touch this with two hands, you're gonna die anyways because you're still completing the circuit. So, sure, it is a safety precaution. This thing is, but it's also there to not fry your house's power as well. So that if any problems happen here, they're not going to be transferred here. Also, the fuse is here. And that is this fuse, this is the switch. The fuse is here as well. It's basically a last resort safety option. 3 amps or 250 volts is way higher than any values that will be going through this system here. So that's the isolation transformer. I'll go into that in more depth later. This is the variac here. There's this dial on top from 0 to 130 volts. And it's exactly what it seems like. It will change the voltage from 0 to 130 volts. And this is also another safety feature. You know, if you want to test your bench on 20 volts, instead of, what this wants is 120, 117 about. So to test your item on a lower voltage, to make it more of a safe environment. So let's look at its schematic real quick. So this from here, this connection to this connection. Also, we'll go deeper into this later. But from this connection to this connection, this variac is not isolated at all. It doesn't have any magnetic field. Well, sorry, that was wrong. Inductors do cause a magnetic field, but it doesn't have strong enough magnetic field because there's no two coils. There's no other coil to receive it. Also, it's just one circuit. So there's no isolation in a variac. This is connected to this. I can demonstrate that later. I can demonstrate that. And now, this transformer. This is the deadly transformer. Obviously all of these work with deadly amounts of electricity, but this is super deadly because it steps up the voltage to 1000 volts, and it steps down the current to 23 milliamps. The reason it does that, I mean, it's an oil burning ignition transformer. Also, yeah, here's this kind of chopped like cord design, but the reason I did this, I had to take apart a 3-prong cord. I ripped off the 3rd prong, and I also cut off the ground wire here, to make sure that this isn't for any reason connected in here. I did learn that the ground in here is actually, it's just like an empty node, basically. It's just a piece of metal, not connected to any of this, not grounded to the case, not any screws, nothing on here. But, you know, just to avoid that entirely, I just took off the ground entirely. So it's just the pure circuit here, positive and negative, and so it goes along here, over here, and then there's actually another, there's another 2 coils on the inside of this to magnetically transfer the electricity into these. And so this is isolated as well. I did check with this multimeter here. It's a completed circuit here. It's not on right now, but if it was, this would beep to check for continuity of the circuit. So there's that. And let's look over the schematic. After we look over this, I'm going to go over everything in more detail. So, also I was running out of room, but also it really does match these. They're technically flimsy, but I'm pretty sure these are 18 gauge or so. And this, they are copper, and this wire here, it was originally meant for like a powerful PC. So it was like 300 to 500 volt rating. So they are suitable for this. At a higher current as well, not just 300, 500 volt in general. Yeah. So they are suitable for this 230 watt output transformer. So when I was inspecting it, sure, regular transformer design, you see those 2 coils, the isolation, the magnetic field, but you see these, see this connection, this connection, this connection. Why are there these 4 other random nodes here? I honestly don't know. So they're connected to this case, and there are 1, 2, this is covered up. This was the 3rd and the 4th. There are 4 connections to the secondary coil. And so I did use the multimeter to make sure that none of these connections, none of these, this, none of them were connected to these, which is the primary coil. So this is still isolated, which is good. But for some reason, the primary coil is, or sorry, the secondary coil is connected to these 4 other connections. But the 2 that technically like matter, I would say, the 2 that I'm going to be messing with are these. And you can see them right here. I just drew them on the schematic to look cool, but really they're just metal pieces. And I'll show you what I'll do with those later. But, you know, that's a pretty intimidating view now that you see that that's 10,000 volts, 23 milliamps. So now let's look into everything deeper. Okay, so the first thing I want to look at is this lockout tagout. It not totally, you know, that's a professional design for systems with capacitors, huge values of electricity. But there is a shutdown procedure. So that procedure is turn off the isolation transformer. So hit this switch here, right? So if this was on, you press this. So now that's, that just, I'll show you on the schematic. We're at 1 here, and that just lifted this from the down position to the up position. So now this is no longer a complete circuit. But to make that safer, you then take this out of the wall. So now the mains power is no longer connected to your system, and it should be totally safe. There's no capacitors, it's simply just coils are the main feature of these. But when a Tesla coil is connected to this, there will be capacitors. So it's going to be a much different lockout, tagout. I use that term loosely because you're not locking or tagging anything out, but you are making sure everything is turned off in the correct order. So then, oh yeah, sorry, that was 2. See, number 2, unplug from the wall. Your system is not powered anymore. Now, you turn off this, because this is the next thing in your system, right? So if this is on, then you just press this off button. So there's this, where is that? Here it is. Step 3 is this switch for the variac, and that will connected, disconnected. So now that circuit is no longer continuous, although the entire circuit stopped being continuous after you switched off this. You still need to do these in the right order. So then you unplug this thing from here to shut that down. And so on the map here, that's step 4. You notice these ground wires here? There's not a huge reason I'm seeing for them. They're not connected to anything, they're simply just there. And so there could be a system where you do need this ground wire connected to for some reason, but in this system, it's just not necessary, and it's kind of just a piece of metal there. But that's okay. So, then step 5, we have this cord here, and then you unplug that. And so, on the back, step 5, unplug the main terminal transformer. So, you notice that it's in like a specific pattern. You turn off the first thing that's delivering power to the rest of the system, then you unplug that. So basically, you safely turn off the first thing, and then you safely turn off the second thing, and then the third thing. You don't start with the third thing, because then you still have all these difficulties, and the third thing, in this case, appears to be extremely dangerous compared to the other ones, because it has these open nodes. There's these, this, and covered up, still this. So this is obviously the most dangerous piece, just by its conductor exposure. So that's the shutdown procedure. So now I'm gonna go deeper into the explanation of like the specific parts of these 3, starting with this one. Okay, so I'm just gonna go over, you know, the schematic here. So first, let's start with the power lamp, the power switch. So basically, we first have these wires, right? Let's see, here they are. These wires right here, okay? Let's start with these wires, right? These are these. And I think I might have had, they might have given me a different order of the schematic, because what I'm seeing right here, right, is that the fuse, this it says 250 volt 3 amp fuse. It appears it comes before the switch because we go here, 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 and then we go around, fuse, white wire, follow the white wire up here, and this white wire connects down at the bottom over here at this power switch, right? And then other black wire at the other bottom. So the schematic I took from the online version, I guess, was kind of wrong. Instead, you know, it should probably look, you know, move this fuse over here, right? And then draw 2 lines here instead, coming from the power switch across these 2 lines. But it's still fine to look at it this way because the switch, I mean, no matter where it is, it's going to continue or discontinue the system. Okay? So then, you know, after the switch continues the system, you turn it on. You go through these wires here. It's not plugged in. These wires here, right? 2 wires. And then this whole magnetic coil. 2 coils. This is the primary coil side here. These wires going in. And then coil, magnetic field, secondary coil. Okay? And then the secondary winding, secondary wires, I want you to see over here, this one connects in to this wire, right? And this one connects into this. I'd say they're nodes, call them nodes. And those nodes correspond to these outlet holes here. And then at the bottom, there's not the best lighting, but at the bottom, I covered up on the inside, the ground node. On the inside, I covered it up. Sorry, the ground node, this bottom hole here. I covered it up with electrical tape because it was really just an open piece of metal. And although these aren't flexible enough to touch each other, I just wanted to cover it up. This piece of metal doesn't connect to anything else on the case. Like, for example, you know, the screws or the case body itself or the screw of this. That would be terrible. So it's not grounded to the case. It's just a piece of metal. I covered it up. Also, if, you know, by some chance, you know, this ground wire gained consciousness and connected itself to one of these, it wouldn't be a big deal. The reason is because then the circuit would just look like this. It wouldn't really fundamentally change anything about the safety of the system, because this is what fundamentally changes the safety of the system. Isolates so that you have this over here not grounded to your house, and then you have this over here, super high power, house power, grounded, copper rod to the ground. This is not grounded, and that is better. That is the correct way for a test bench. So, after that, these 2 wires from these 2 top terminals, this top terminal goes under. See that wire on the bottom? It goes under to this other side. Here, let me reach through this other side. And then the grounds aren't connected to each other. It's just a ground wire, just a little piece of metal here, not connected to anything. And then the top 2 are connected to these top 2. I'll show that with a multimeter test. And I'll also show with a multimeter test that the system is here. I'll show with a multimeter test that the system is isolated. So, first of all, we have this, and then we have this. That's continuous. We have this, and we have this. That's continuous. That's continuous, okay? So 1, 2, 3, 4. So you can see this, if it was a schematic, it would be like this, and then like this. So 4 connections connected to each other, and then just 2 grounds, not connected to the secondary, just 2 pieces of metal. And you can actually see that. You can see it right here. This is the ground I'm talking about. I forgot to go back to the thing. That's the primary coil, secondary coil, and then the lamp. The lamp tells you if the secondary coil is receiving energy. In this schematic. In this schematic, it's different. The lamp is actually only activated whenever it's continuous with the power switch. So also this lamp works, because if you have this power switch on and this is plugged in, then this is going to be transferring power over here. And if this was over here, right? If this was not on the primary side and on the secondary side, and this power switch is turned on, it would still light up because the magnetic field is transferring electricity. So, one more test, by the way. Leave this in here, right? That's this. You need to make sure that it is not continuous with the secondary winding, and you need to make sure that the primary winding, okay? Also, I'll show you the grounds they're not connected to anything. Not this, not the chassis, here. Balance that in there. Not the chassis. Nothing, they're just pieces of metal in there. So, here's your secondary winding connection, and then the primary winding connection. Here, hold that up to the camera. Ugh. Here. I wanna show you that this is connected here. Here, I'll put it on the ground and then do it. There. See? So these are isolated. And then to show you that the other prong of the mains power actually is continuous, right? I'll balance this. I'm trying to do this with like just my hands here. Look at that. That's balanced. Continuous. See that? And it's not because they touched each other. Here, I'll do that again. Make sure they don't touch each other. Right? It's because this mains outlet is continuous. Oh, this is hard to show. Okay, that's connected. And God, sorry. Gonna take a second. Okay, got it. There it is. Okay, I showed it. This is, well, obviously this is going to be continuous with itself, but the most important thing was that these are not connected to these. So that is the rundown of the isolation transformer. Let's move on to the variac. Okay, so this was the most I could take the variac apart. Because this thing, I pulled on it, but I didn't want to pull super hard on it to break it. It just doesn't seem to want to like come off. Also, you can see here that it's kind of like stopped from turning because of this this contact. And now we can get a much better view at what the variac actually does. So it is one coil, right? One inductor, which raises or which manipulates the voltage and current values. And then it's all of this here. And then the rest, where is it? Yeah, that's pretty much it. So there's no two sides to look at. On the other side, it would just be more coil. So whenever you turn this around, it engages more of the magnet wire, of the coil, more steps of the coil. And so there's an equation, I forgot exactly what it was, but there's an equation that says the more coil turns you have, the higher your voltage multiplier is going to be. So the more you engage the coil, the higher the voltage, and so that's why the voltage goes higher as it goes further around the coil. So right now it's just engaging like just a few wires, just a few turns of the coil. It's like 50 at that point, and then so on. So I don't want to give that a lot of friction. I want to be careful with it. But we can look at this part. And also check its continuity. I do understand that looking at the schematic right here, right, it is just one coil. This coil does have a capacitance because, there's space on the inside of it, but that doesn't really change much because it is still just a one coil. It's just one coil, no insulation. And so I could honestly stop it there, just understanding that that is not a safety feature, but I'm going to explain it. So there's a switch here, and that switch, let's see what it's connected to. You know what, let's start at the power cord right here. So there's a ground and live wires. So we go and go down the wire and here. So I would assume that this bottom green one connecting to the bottom over here, let's just check that continuity. I'm gonna put my camera down here, and then and then carefully check the continuity. So I put one here, and then on the other side, you can't see this, but on the other side it's connecting to this green. And the multimeter isn't on, sorry. Okay. And that is continuity between this ground right here and this green ground on the other side. Okay? So that means instantly, that tells you, right, that this is not an isolated system. It just goes straight from its power source to its delivery. But that's okay, because the point of this isn't just pure isolation. The point of this is voltage control. So then we can right here. So this is that. And then we have the two other, this brown and this blue. They're connected over here to the switch. And that makes sense because the switch, here. So these two, right? I was right about that. It's this brown and the blue connected to this. It says the fuse is first and then the switch. We can check that. Check it for accuracy. It looks like the switch. Yeah, the switch is actually first before the fuse. Okay. So you can switch that up in the diagram, but the order, I mean, once again, the switch is just there to have continuity. So wherever it is in the system, as long as everything is connected, it's fine. So, at least for this system, it's fine. You know, I don't know about other ones. So, after that, you know, we go through here, then this coming from the ground, so these are connected, I would assume. And so the switch design here is wrong too, then, because this is clearly 3 connections. But once again, it's still continuous. And then that goes over to the fuse after the switch. And then the fuse goes into the coil. Okay, goes into the coil. I don't see where it goes after that, because it's just hidden. But connected to it is this piece at the top of the coil, taking the power from the windings. And then this piece coming from another piece of the coil, which I'm pulling on. I'm kind of slightly damaging the coil by just having this down, actually. So I should probably put this back up. This blue piece connects to this power terminal on the outside. Which also connects to this voltmeter. So let's go over here. There's that voltmeter. These power terminals. And that's pretty much about it. Yeah, the variac is pretty simple. And you know, there's no bad solderings in here. Everything looks pretty good. It was just a little bit in a different order than what's on the schematic here, but it has the same function. It has the same function. So that's the variac. Okay, at last is the main terminal. So this thing here, it asks for a 250 volt amp, 250 watt input, 60 hertz, 120 volts. 60 hertz, by the way, is low for electricity, but it's the regular house hertz. It's like electricity switches directions in alternating current 60 times per second. In a Tesla coil, the resonant frequency will basically just skyrocket up to hundreds of thousands of hertz. So this is the low hertz, and so low hertz is actually a lot more dangerous because it's low enough for your body, your nerves, to be able to register and electrocute you. Super high hertz, not right away, and it's not that black and white. There's also the skin effect, where electricity goes over the surface of the conductor rather than the whole body of it. There's stuff like that, but it's not something to be dogmatic about. You gotta be careful. Anyways, this is stepping up from the primary to 10,000 volts, 23 milliamps on the secondary. So, you know, similar amount of power, wattage, but an insanely higher value of voltage, much lower current, 23 milliamps versus, I'd say like 120, maybe like 2 amps or something, probably, is what this takes in. So I did modify this wire here, so that it's just the 2 prongs and there's no ground wire, because this thing didn't need a ground wire in the first place. Going over to the schematic, its input doesn't even have a ground. It's just that. And then it goes up to the magnetic field, primary to secondary coil, and then over to these. So, there was some weird continuity things. Obviously, these are continuous with these, but these two, they're not continuous with these. Obviously, the most important piece, and which I will demonstrate right now, just that thing. That's good. And then, so we have this here connected to this, and then over here we got, see, these are not continuous, but this is continuous with this. Oh, sorry, it's not turned on. My multimeter isn't turned on. This is continuous with itself, but it's not continuous with the secondary coil. So that shows that the insulation is working. It's the magnetic field is, the magnetic field is not working, but because it's not plugged in. These are continuous. What? Oh. Okay, so for some reason, it was only showing values on my multimeter. See that? There's the multimeter. I touched these. For some reason, some of these were only showing continuity values on the multimeter. And then you see that screw on the side. It shows up as a resistance number. And there's some screws on the side and the back over here. Here it is. Where is it? I think I found it. Oh no, there it is. Got it. And then there's the value for the screw on the back. And it was here, but, sorry. It was here, but I covered that up. And so these are continuous with some screws on the case. That doesn't bother me much because, you know, it's not necessarily a safety hazard, compared to like this being a safety hazard. Like these are just open live pieces of metal. And so the screws on the case. I mean, you just obviously whenever this turned on, you just have to stay away from it. Is the essential idea. So let's go back. Let's go back to review this. So I was showing you the continuity here. One of these is covered up on the back by tape, but these two screws on the front and this screw here are open, and then those were the two nodes, basically, and this is just a little plasma drawing. Here's the model of it. It was already on 2721 is the model? Is it? Yeah, that's the model. So, also I couldn't take it apart, because for some reason this here, whenever I got this from eBay, this seemed to be burnt off. One screw seemed to be burnt off, and another screw seemed to be burnt off. And at first it was unnerving to me because I was like, why is that? Why can I not open it? But whenever I did the multimeter check, it seemed totally fine to me. I mean, I've shaken this thing around. Nothing happened with it. The continuity didn't change. So, as far as I'm concerned, the multimeter test was enough for it. Plus, this thing doesn't have to be continuous. Or sorry. This thing doesn't have to be isolated. The only thing that has to be isolated is this. Because whenever you think about it, this entire page here is the test bench. And everything off the page, coming from this alternating current point, is the house's power. Okay? So technically, nothing on this bench here, besides the isolation transformer, has to have magnetic isolation. I guess it's a plus that this thing has it, but I would never plug a main terminal straight into the main terminal. because that's just completely dangerous and just deadly, honestly. Having these is like a given for a test bench. So anyways, that's the rundown of the 3 pieces, and now I'm gonna show them all together. Okay, so this the isolation transformer, by the way, is not plugged in. So the test system is not plugged in. Let me just put on this glove here. It says these are rated for 12 kilovolts, but it doesn't say, or at least I can't read Chinese, but it doesn't say a current value, so honestly, I don't know what to say about these. Maybe I should get a translator on there. But here, we have this, yeah, this is just, by the way, it's not plugged in, it's just a demonstration. We have this PVC pipe. And so I looked at a polyvinyl chloride versus copper, a comparison of like this insulator versus conductor, just to see how it could work as a discharge rod for, you know, testing conductors. And so the material itself, it's a very good insulator, but the paint on it, I have no idea what material that's made out of. So I need to figure that out. But in the meantime, there is this electrical tape, Lego piece, copper 18 gauge wire. Let's focus. It's just a wire. Here. And the other side of that wire is connected to one side of the main terminal, the 10 kilovolt terminal. And so I can back up and sit down. See, I'm sat down on the ground here. And I can back up all the way over here and safely, from a distance, as long as I know what that paint material is, safely. This is actually really hard because I have to balance this thing. I'm like at the end of it. Hold on. Let me get a bit closer. So that I don't, by the way, I'm on the ground so I don't fall down and, you know, electrocute my face on the main terminal. I'm actually a distance where I can fall and still be safe. I can safely use this copper end of the wire connected over there to do this. Bzzz. 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 And so I don't think it's going to go this high. It might go about this high, right? And so that's a pretty good length of a plasma arc coming straight from a transformer with no capacitor bank, no spark gap, no primary coil, no secondary coil, no breakout node. Sorry, I just explained the entire schematic of the Tesla coil, but oh yeah, don't forget the grounding for the secondary coil, but anyways. The plasma arc is not going to be super big, but it's going to still be pretty sizable because of the amount of power here, 230 watts. That's nothing to mess around with. That can easily kill you instantly. So you have to step back, still hold these gloves. I need to make sure they're actually good gloves. I need to make sure this paint isn't a conductor. But you can step back from this safe distance sitting down and just bzz, 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 and that's the first test. So yeah, you know, I plan on making a whole huge Tesla coil, at least medium size, not huge. You would need a scarier transformer for that. But this can make a pretty good sized Tesla coil. And yeah, I just need to make sure it's 100% safe before I test this piece of the system. And then after that test is successful, then I can move on to the next stage.